Welcome to our workshop. We're going to be talking about how to do a quantitative XRF method for pharmaceutical analyses. We're in the Woodlands, Texas, just north of Houston, and this is just a picture of our applications lab. We're going to be working from one of these Primus 4 or 4i bays. We're actually in another one where we'd be looking at that picture as it is right there.
But before we get into the actual workshop, we're going to spend about 30 minutes or so going over the theory, and then after that we'll go into the prep lab to show you some representative ways of how we do some sample prep, and then actually apply that to the methods and put it on the system to show you routine sample analysis.
I'm Glenn Williams, by the way.
Oh, and I'm Thanh Nguyen.
We didn't introduce ourselves. So this is a set of our instruments, and if we click down, this isn't even the full set of XRF instruments. So, you know, it can be kind of dizzying how much there is to choose from. What we're focusing on this is our, kind of all-purpose 4 kilowatt wavelength dispersive system. We'll talk about what that means as opposed to energy dispersive, but we have a variety of energy dispersive systems as well. Again, we're focusing on this one because it's something that we can do basically everything on. These ones we have very focused kind of applications that we've talked about in other areas. So X-rays can be used for single crystal, for X-ray diffraction, powder diffraction, computed tomography or imaging, and XRF. So obviously it's a lot of different things that X-rays are used for. But really, what are those? What are the kind of specifics? What's the differences between those? Well, most of these other techniques, the single crystal and powder diffraction, you're looking at structures. So you're looking at a repeated pattern, and you're figuring out what the molecular structure is, or what the phases are in a particular powder sample. With imaging, this is transmission. So transmission basically through materials. They're absorbed to different extents, the X-rays, and so that can be used at different points if pictures are taken to look inside and all around samples without even opening up a bottle. So that's CT, and then X-ray fluorescence is basically elemental analysis. So we can look at what elements are present and how much of them are present in a sample. So what we're going to do at this point is go through the fundamentals of X-ray fluorescence, just to give you a good kind of basic understanding of what we're doing, why we can do this as a direct analysis technique. And then after that, we're going to take you into the lab, and Thanh is going to show you different ways that we can prep pharmaceutical materials for analysis.
But we're going to keep this really basic, high level, but if you want more in-depth discussion or conversation about XRF and particularly about your samples, we'd be glad to have a one-on-one session with you.
So just in the simplest sense, what we like to do when we teach a school on this is we try to put things in a perspective of a visible thing. So if you look at qualitative versus quantitative, if we kind of take the visible spectrum as an example, we could have a compound that's blue and one that's red. So in other words, you have a chromophore, you can actually see the difference between those two visibly. And we can tell qualitatively which is which. And if we were to take a set of standards, we could see quantitatively by the changes in intensity of that particular color. If we do this with X-rays, obviously you'd be looking at essentially all white materials or all blue. Like, you don't see that difference visibly. We use the X-rays through the fluorescence to do the quantification of those materials. But we have to teach a machine how to do those. All of our machines that you saw on the previous slide have a set of semi-quant capabilities because a factory builds in or teaches the machine for a wide range of materials. But when we're looking at your specific application, we want to teach it to a really refined level. And so we have standards and we develop calibrations that way. So how do we do that? Well, we have a whole set of concentrations. You have materials where you put in different levels or amounts of drug or amounts of metals, and then you're getting intensities for those. We then just do a linear regression, and we get a calibration curve. Of course, software is sophisticated and can do all this for you. We then run unknown against it, interpolate that against that regression, and then we get a concentration that we get as a known value. Okay? The nice thing about XRF is these calibrations are stable. And as we show you after we do the prep section, I'm doing a lot of talking right now, but she's going to steal all my thunder when we go to the prep lab, and she'll be doing all the talking.
But the key thing to the calibration that it is stable. You don't have to redo it, every day, just like in chromatography. But these systems are extremely stable, and they will maintain it for years if you drift the method properly.
So now here's a case where we were doing the red and the blue, but now all of a sudden we have some purple sample that maybe is a combination of the red and the blue. And what we're trying to do here is illustrate what are the two main things that we have to kind of take into consideration for X-ray fluorescence, which is a direct analysis technique, as opposed to something like chromatography where we're separating out the materials and then looking at them. Here, we're not going to bother doing that, which is a real benefit, but we then have to take into consideration the fact that all these things are together in the sample, and how do we differentiate them while they're together. So we have two things that we have to worry about. One is resolution, so being able to resolve the peaks of the two sets of materials. And also the other is what we call matrix effect. So the presence of the one, what does that do in terms of absorption of the other, and vice versa? And
that's something that customers tend to forget, is that the matrix is still there. You have to account for it. So unlike traditional chromatography, which is my background, I used to do mass spec, so I've always extracted it out, and it's always like a solution that I've removed the matrix. So in XRF, the matrix is still there, so you have to remember about that and account for it when you're doing the analyses.
So let's talk about matrix effects. Well, this is an example here. This should put it into a visual perspective for you. If you have cadmium, let's just say one example, cadmium at 100 ppm concentration in 4 different types of samples. Okay, the first 2 types being polyethylene. And the only difference here being polyethylene that's a thin sample and polyethylene that's a thicker sample. Well, when there's an element like cadmium, which is a fairly heavy element, it has high energetic or short wavelength X-rays. And so those X-rays can travel through a large distance. And so we get more signal if we add in larger amounts of sample. When we move to something like aluminum, which is a little bit heavier material, it's a metal, but it's a light metal, we get less cadmium signal, even though there's 100 ppm still in that sample. So we can't calibrate for polyethylene and then run for cadmium in aluminum. We would want to have a separate calibration for aluminum. Or, as we'll talk about later, we'll take into account this matrix, we'll analyze for aluminum, and then know how much aluminum's there, how much it would absorb the calcium signal. And then furthermore, if you go to something like copper, you see that's even a heavier metal, and then that will absorb the cadmium X-rays even more. Even though there's still 100 ppm, we have now much less signal. So we have to account for that change in the matrix. And you can imagine if I use something like lead, we'd have even less cadmium signal, because the X-rays from the cadmium can't get out of the lead as easy, so it's just really a surface analysis of that. Fortunately, for pharmaceuticals, you have very light matrices. So you get a lot of signal, you can get a good depth of analysis, and you can get good low detection limits for most of the metals. So now, here's another example in terms of the absorbance of these X-rays and why matrix effects are so important. If I were to take something like cobalt, so we looked at the previous example of cadmium. Cadmium X-ray is extremely energetic. Cobalt is still a fairly energetic X-ray, but if we put different films in front of the sample, so the X-rays that are incident on the sample, those are energetic. They'll get into the sample, it's a spectrum of X-rays, and then it will excite cobalt in the sample. But those X-rays have to get out in order for us to detect them, the cobalt K-alpha X-rays. If there's a film on top, they will be attenuated slightly. So if you look at proline, etnom, kapton at micron levels, they will slightly attenuate the signal. Now, if we look at that in comparison to aluminum, aluminum is a lighter material, a weaker X-ray. So now, if I go and I add films in front of that, I decrease my signal more. So we like to run these samples in vacuum. We like to run them without any kind of films, and we can maximize our signal and still get very low detection limits for even the lighter elements.
And when Glenn is talking about these elements here, we're talking about the Z number on the periodic table. So that's one thing that when you're doing XRF, you have to consider about the element, what kind of wavelength it has, whether it be weak or strong, and then how it gets affected when you do the sample prep.
Right. My background was in organic, so I knew about 4 elements on the periodic table. Now, since doing this for a while, I know a good portion of it, and so just you consult with the table and go, oh yeah, that element's light or that's heavy. And actually, there's a lot of good guides to show you what kind of signal you get and what the wavelengths are. It's all known quantities. So then, if I take something even lighter like fluorine. Fluorine, you can see, is decent signal when there's no film, but as soon as I put even a proline, which is a light film, at a low thickness, I still get a huge reduction in the intensity of fluorine. So those are all things that we consider when we're doing these things. Fortunately, again, for pharmaceuticals, for the most part, we're looking at heavier elements, and we're looking at a very light organic matrix. So you maximize your signal. Now, we've mentioned wavelength dispersive technology and energy dispersive. We show the different machines, and that's where I think it can be confusing for people just starting to evaluate this technique. So we're going to go into a little bit of what that means. Well, here we talked about matrix already, and we said the other thing that we have to deal with, which you have to deal with almost with most analytical techniques that use the electromagnetic spectrum, is that you have overlaps. So resolution is something we're trying to always maximize in analytical. And, the case of, again, going back to light, if you had this purple material and you're trying to separate out the blue and the red components, if you had a prism, you could separate those out, and then you could quantify each amount of the red and the blue. Well, it's the same thing we're doing with a wavelength dispersive XRF, radiating that sample, producing those fluorescent X-rays. They're all coming out. And then we use diffraction, which is like a molecular diffraction grating, right? By using these crystals at different angles, the position of the detector at different positions, and we can then separate out the individual wavelengths or energies of the elements that we're looking for. And so here, just in a quick overview, difference between wavelength dispersion versus energy dispersion XRF. Energy dispersion, the nice thing is we're looking at all those elements or lines from the elements at one time, and this solid state detector is doing the separation of the energies. And then wavelength dispersion, of course, wavelength and energy, it's an inverse relationship. The longer the wavelength, the weaker the energy, and vice versa. We're using the separation of the wavelength via diffraction. So the crystal is rotating at these positions that we talked about, and we're able to get separation before it reaches the detector. Now, the benefit here is it allows us to use different detectors so that we can get lighter element sensitivity, and then the other thing is we can improve our resolution. So here you're getting more elements at once. They can be very compact systems because the optics can be coupled closely. With the wavelength dispersion, we get better resolution, better light element sensitivity, but the machines become bigger. And that's the kind of the balance that we draw. This is just an example then of the same 5 samples run on our energy dispersive system versus our wavelength dispersive system. And if you're a visual learner, you can see this right away. Well, the same 5 samples. Here I have difficult.
It's only 4 samples. Just 4. It's okay.
I'm going to redo that. Why does you have to do that?
I'm sorry. You get the same 5.
Like, I'm not going to redo it. I was going to redo this. This is live. What can I do? No, so these are the same. Should I redo?
Yes.
So moving on, the boss here, you know, hey, what can we do? Live TV.
I have to keep him on track.
Yeah. So here, the same one sample, you can see again that resolution difference. You know, here nickel, the cobalt K beta. You know, I can't see it in this spectrum here. So it shows you the difference that you get by switching to a wavelength dispersive system. Again, though, for each of these elements or lines, if I were to look at, I would have to sequentially analyze these. The advantage of the ED system is I'll get all these at one time, or at least a group of them. So in the ED systems, we use filters. But it's not truly like all simultaneous, but we get groups of them at one time. So advantages of both systems. If we're really trying to get down to really low levels, we're going to switch to a high-powered wavelength dispersive system. And if we're looking at light elements, definitely a wavelength dispersive system. So when we're talking about X-rays, for XRF, we're in what we call the soft region here. So that's from 1 angstrom to about 100 angstroms, which corresponds to, again, remember, inverse relationship between wavelength and energy. That corresponds to 12 keV to about 0.1 keV. Again, I've said it already, it's just inverse relationship. We tend to use these terms interchangeably, and if you're on either side, you know, there's kind of the ED guys and the WD guys. We're both, so you know, we go back and forth between whether we say, oh, it's short wavelength, or it's long wavelength, or it's high or low energy. So now, to give you a perspective of what's happening here, how we're generating these X-rays. Well, we're using X-rays, and if you have something like an SEM, you might be using electrons to generate X-rays. And in fact, that's what's actually happening within our X-ray tube. But essentially, we hit the sample with a primary X-ray beam that's a polychromatic beam. If the X-rays within that are of sufficient energy, they will knock out the inner shell electrons, which will be lost as photoelectrons. That will leave an unstable state. The outer shell electrons, which are less stable than the inner shell, they will fall, they will fill that void to make a more stable state. In doing so, they will release the difference in energy between that outer shell and the inner shell, which will be lost as a fluorescent X-ray. This is a little video demonstration of it, and a cartoon. It doesn't really happen like that, but just to give you a perspective. So just to show it on a kind of spectrum here, we have different energies, right? We have a polychromatic source. Now that source is dependent on a certain anode. So there's a certain target material that we call within that X-ray tube. In most of our systems, either like palladium or rhodium, kind of a middle Z element, allow us to excite, you know, the whole spectrum. Well, most of the incident X-rays are lost as heat in the sample. A certain amount produce fluorescent X-rays. If you have a highly ordered sample, you could get diffraction. That's really only the case in situations where maybe somebody's analyzing semiconductor wafers or highly oriented materials. And then we can get transmission through the sample, as well as one element that's producing X-rays can excite another element in the sample. And this is the absorption or the enhancement that occurs. These are what we're talking about, the matrix effects. We can also get scatter from the X-rays itself. Well, if I have a palladium X-ray tube, I'm generating palladium characteristic X-ray lines. I'll see that in the sample. And where you might think that's a detriment, it's actually, we can use that as an indirect measure of how heavy or light our sample is. So we get different amounts of scattering. So all this kind of stuff we can use to our advantage. Okay, so one of the things we can do with our system, we can change the power of the incident X-rays or the power of the X-ray generator. So if we have high kilovolts, high potential, we can kick out inner shell electrons of higher Z elements. So if we don't have sufficient energy, then we won't kick those inner shell electrons out. We might kick in one of the outer shells, and so we'll end up with just, let's say, instead of the K lines, will produce L lines. So there's different lines that are going to be produced in a sample, depends on what element. In many cases, there's multiple lines that we can be looking at, and then we can decide based on the energies of those lines how we're going to use them. So there's different power considerations to make. The machines do all this for you. The nice thing is we can tweak all these if we want to make a custom method. And as Thanh was saying before, once you make that custom method, it's saved on the machine for years, and we can just recall it and run a sample 4 years later when you get the same result.
And we'll show all this during our next session when we are actually on the instrument building the methods, where you change the power and you'll see the differences in this.
It's just going to be a little background, so when we go in and we do those things, it gives us some perspective. Yeah. For the lighter elements, we can go to lower kilovolts. We keep the same power, so power is the kilovolts times the milliamps, or the potential times the current. And if we go to a lower kV, we don't need as hard of an impact. We don't need as high of an energy to kick out that inner shell electron. So we can, get our total power the same. We can increase our current. It's basically like having more punches. Okay, so for silicon, we can drop that to a lower kV, increase our milliamps, and get more signal. And then you can see that even more so with something like carbon. Now, you might ask, well, if you're using that palladium tube or that rhodium tube, how do I analyze for palladium or rhodium in my sample? It's a good question because, like I said, we do have those characteristic lines from the tube. Well, all we do is, before the X-rays hit the sample, is we essentially put a filter in place. And that filter will block out that section of the spectrum, the incident spectrum, that has the palladium or rhodium X-rays in it. And that allows us then to still excite that sample with the X-rays that get through that filter, but it won't produce those scattered lines. And so if there's palladium or rhodium in our sample, they're truly coming from the sample itself.
You can see here this red line here. If you zoom in on it, you can actually see these elements here when you put the filter in. Because if not, you're not going to be able to, because it's under the Compton array like scatter peaks here.
And this, of course, is all done automatically in the software. Okay, so that I should give you a good general perspective of how XRF works. Obviously, there's a lot of little details to it, and we teach all those kind of things in schools, but it's pretty easy, and you don't have to actually worry about all that to run a sample, to run a method. You just think about it as another detector. And Thanh came in here from a mass spec background, at first she's like, well, I don't know anything about X-rays, but it's an analytical technique. So it's like any other analytical technique, it's just a different detector. So, like we said in the beginning, to do a calibration, we just need a set of standards. In a lot of cases, what we do is we just spike standards. We use ICP standards if we're doing metal analyses. You might put in different amounts of API. However those standards are made, we get a set of calibrants. We then generate intensities of the X-rays of those calibrants, and then we get a linear regression. It's actually very simple. Once we do that, we can run unknowns, interpolate, and get a result. Now, as we talked about matrix effects, in general, your pharmaceuticals are not going to have very significant differences in the matrices. But if there's one formulation a little bit different than another, what are the heavier materials? Any kind of organic change is not going to make a difference for the kind of elements you're going to be analyzing.
Because that matrix is really light. So we've had people approach us, well, it is changing, but you're changing, your matrix is so light anyway, going from a light to another type of light matrix, it's still the same.
So kind of the substitute matrix that we tend to use for organics is just cellulose.
Right.
However, if you have formulations, you have iron oxide, you have V-gum, you have these different materials that have heavier components to it, titanium dioxide, well, we have a couple choices. One, we can do a calibration on a specific formulation type, and we just have multiple calibrations. Again, they're saved on the system. Once you make them, it's saved for years. And you even have ways to kind of correct for any kind of drift that might happen over years. The other option you have is to do what we call a fundamental parameter application. Okay, and as I talked about here with the aluminum, as we go from a polyethylene with cadmium to aluminum with cadmium, we see this change. I can't calibrate with this and then just run an aluminum sample. I'm going to grossly underestimate the amount of aluminum because my signal drops. However, if I do what we call fundamental parameter method, means I can analyze for aluminum, I can analyze for copper, and depending on how much of these components I have within that, it will compensate for the fact that we expect to see a lower amount of signal for that analyte depending on how much of these are present. And if we incorporate those elements into our calibration, you can make a fairly universal calibration to cover so many different types of formulations.
Right, so the key here is to describe your entire matrix. If your excipients are changing or there are heavier elements in there versus just cellulose or lactose, it is changing. You have to account for the entire thing because you're not extracting it out. We are analyzing it as a bulk.
And this is just another illustration of empirical versus fundamental parameters. Let's say I were to take something that was purely organic and it had analytes of like arsenic, cadmium, lead in the sample, represented by little green dots here. If I add iron or iron oxide or some type of iron-containing material, I will now, some of those X-rays will be absorbed by the iron in the sample. Well, I can't calibrate with this and run on that, but what I could do is do a calibration for formulation 1, formulation 2, and formulation 3 that maybe said had more iron in it. That's what we call an empirical calibration. We could do separate calibrations. Again, they're saved on the system. Option 2 would be, hey, let's run for all these elements, but also let's analyze for iron as an analyte as well. And depending, and this could be up to mass percent levels of iron. Depending on how much iron is, this calibration is to compensate. It's basically an algorithm that will then determine the appropriate accurate results for those analytes, even though the iron amount is changing in the sample. And so you have that option to change. So this is an example of a pretty drastic case where maybe the matrix is changing much more significantly than you would have with a pharmaceutical material. But take steel, nickel alloy, there's changing different amounts in mass percent of the different metals in the sample. If I do strict empirical, no corrections whatsoever, the calibration is, moderate to bad at best. But if I incorporate and I take into account the variation in all the components, and I'm not looking at just specifically one analyte at a time, we can get extremely high levels of accuracy by running this fundamental parameter method.
Now, but through the software, if you build it with one method, you can change it to another method by just a click of a button without reanalyzing or recollecting anything. So I really like the software in the sense that you can do that without basically re-injection, if you're in chromatography.
It does all this for you. So although it seems kind of, complex,
right.
It's not. And you, again, always have the option to just, hey, my formulation is constant. I'm just going to analyze for those analytes and do a calibration strictly empirical, and that's the easiest way to operate. So how do we do it? We'll show this again. We're going to go back, show you some different prep techniques. Then we're going to go on the machine and we're going to show you live how we actually do this, and we're going to set up a calibration with you. Essentially, all we got to do is set up a number of standards. This kind of how many standards would you use? It follows normal statistics. Well, how many degrees of freedom do I have? So I would pick n squared plus 1. I have a slope and an intercept, so ideally you're going to have, at least 5 or 6 standards. And then depending on, are you doing any other corrections, we might go up to 9 or more standards for a calibration. Okay, so let's just real quickly, we're going to walk you through what steps are you going to do. Well, you're going to enter your standard values, you're going to determine what elements you're looking for, and then all we're going to do is the software is going to tell us what crystals, what it's going to do all that. We don't have to set anything up, it's all automatic. It's going to have default conditions, but what we can do is if we really want to tweak down to better levels of detection, we can optimize those conditions very easily, and we perform these 4 steps for each element, again, only one time. I'm going to do that. It might take an hour to set up a method.
But that hour is spent very wisely used because you are not going to do this again. Once you set it up correctly the first time, you don't have to go back and do it again. So I call this part, the OMCs for short, is at the heart of your method. If you set this up correctly the first time, you're pretty much good to
Never
go.
have to do it again. And then all you're doing to run samples is take a sample, put it on the machine, run it. Okay? So this is just kind of going through what we just said.
And then you're doing this as the user to optimize it to the way you want it to, with the counting time, make sure you account for all the matrix that's in your sample.
These are the slides from our school, so this kind of tells you what we go through when we're teaching. So all we do in here is we tell the machine it knows what standards we had just put in that table. It says, hey, load these ones up because I know these are high and low levels for each of these elements that you're looking for. Okay. And then what you're doing is you're looking at that scan. You're picking a peak position, a background, peak position and a background position, setting how long we're going to analyze for that. Okay. And then we're going to step two is our background point.
Basically, these are just all the steps that you would just have to pick once you define it.
Again, there's default conditions already come in the system. We're just going, hey, well, I want my background here. I want to collect for this amount of time. And there's even a tool in the machine that helps us to determine how long we need to count, because it looks at the scan and says, well, based on the scan and based on how long you say you want to count, this is what your detection limit is going to be for that particular analyte.
Yeah. Basically, once you pick the peak in the background, this third step is to pick the counting time, because you don't want to waste too much time spending on a peak that has really high intensity. You want to save that time for the one that has lower concentration.
So we pick our peak, our background, and then we're going and we're using this nice tool here for it to determine how our detection limit is going to be or what level of precision we're going to have.
And it will tell you the detection limit. So this tool, basically, you play around with the time so that you can meet your detection limit, your quantification limit as well.
All right, and then the last step here, without getting any kind of detail, and this is a very easy step actually, it's essentially our detector window. If you do chromatography and you use like a photodiode array detector, you're picking what wavelength you want to use. It's not the same as that, but it can be thought of in a similar way, as that I'm picking my energy window. So what I want for it to allow in. So if I have a higher energy, a second order radiation that's coming through, in other words, half the wavelength of the element that I'm looking for, well, that's of higher energy, so I can exclude that information in at the detector.
So how I relate to this with mass spec, for all those out there in the mass spec world, is it's kind of like you're doing the collision cell energy. You want to just focus in on that narrow window area and then exclude out all the endogenous interference with the noise. That's why we're putting these limit ranges, or the lower limit and the upper limit, to just focus on that energy window right there.
Usually the defaults are really good. This again allows us to go in and optimize as we wish.
Right.
Okay. All right, so now the last step is we've optimized everything, we put our standard values in, and we just got to run standard. So the machine goes, hey, load up the standards you had, hit start, collect the data under those specific conditions that we just told it, and then we generate a calibration curve that's all, again, in this kind of linear stepwise way of creating a method. If the calibrations look good to us, we hit save. If we want to deselect points, we literally just click on the graph and then recalculate, and then we can see our squared and any kind of changes to the calibration.
Now, if your matrix wasn't changing, you can do the calibration as is without any corrections, as what we're showing here. Okay, and then if you hit recalculate, it'll tell you what the calculations are of the standards versus your theoretical when you've entered it in. And that's your
R squared. R squared. And then we have the option to build in corrections. And these things are just ones that, maybe we have two elements that are overlapping slightly, or we want to use a different line to correct for that. We can build all these into the system quite easily with the software. In most cases for pharmaceuticals, we find there's very little corrections that we have to build in. But it's all part of it.
But if it's there and you need it, the software will correct it for you.
Then the final thing is, hey, I'm going to use this method. I've just spent maybe a couple hours building it. but it's something I'm going to run for years. And all I want is my analyst to just walk up, put samples on the deck, and hit start. And it's really that easy. But we can make sure that these calibrations stay within spec for years and years if we establish what we call our drift correction sample. And what that is just a stable material that we have an intensity of. It doesn't even have to be a pharmaceutical material. It could be a piece of glass, something that has those elements in the intensity range of our calibration. And so essentially what we're doing is we're establishing a baseline when we make the method or soon after making the method. And then that establishes what the reference intensity is. And then at various points, we can do a drift correction, which means we run that same sample. We get the measured intensity or today's intensity, and then it will set a coefficient to our method. So these are just some examples of drift correction samples. Again, they don't have to be a pharmaceutical material. In fact, it's better probably than not. You want to pick something that has a glass. In fact, we even make some of these things or have places that can make them, and they just put in different amounts of those elements of interest into a glass material that's stable for decades, and essentially just bring those out when you want to drift the method.
And the reason why they can be another type of material is because it's an intensity-based correction.
Right.
So the glass samples here, they are pretty stable, so that's why we're recommending to use this.
We've even used check samples as this. So
right.
It's once that intensity is interpolated and gives you a result, you just make sure you're always getting that same result. The final thing that we can do within this is you can all set this so that it can alert your chemist, your analyst, when they run samples that you're either out of your calibration range or you're out of the spec of your particular analysis. And you can make up as many of these limit ranges as you want and test against that. So if you have certain specs for one type of formulation or one material, and you have another spec for another, you can set those different limit ranges. It essentially makes a daughter method, and then you run against that spec, and it will, as Tom will show on the next slide here, it will give you a very clear indication of whether you're in or out of that particular spec. So if it's pink with an L, it's too low. If it's red with an H, it's too high. And if it shows no color whatsoever, then it's within your spec. Very clear signal to the chemist running.
And it's widely used for the quality control environment, so you'll see right away whether it's within your spec or not. And then it also trends it for you as well. So if you set it up for your check samples or even your drift, it will trend it for you just like you would in Excel, where it draws your acceptance or your specs.
All the control charting is all within the system.
Okay, so now that we finished the theory part,
She's going to do all the talking.
Yeah, I'm going to do all the talking in the sample prep part. So we're going to take you back into the lab and just show you just representative ways of how we prepare things.
And then after that, we're going to come back, and I'm going to do all the talking. No, we're going to come back and we're going to show you at the instrument. We're going to do an application together. We go through all those steps we just talked about and show you how easy it is, and then how you would just set up samples, in perpetuity. The analyses that your chemists are going to walk up and run on the system.
Hi, welcome to the Prep Lab. We're going to show you some simple sample prep for your applications for your pharmaceutical needs. The traditional way is to press a pellet. So what you would have here is some pills. We're just going to go ahead and pour that right into the spectral vial, put some ball pestils in, and you would shake this in a Resch mill or any mixer mill. Once it is mixed, it will look like a fine powder like this. All right, and to make the pressed pellet, we would use a die assembly similar to this. You would assemble it, put one of the dies in, pour all the powder in, then sandwich it with the other die assembly, and once that goes down, you would press it in either an automatic or a manual press. Once that is pressed, it will look something similar to this. Now this is a traditional pellet that you could just analyze directly on our XRF instrument. Now another alternative way, which is a little bit easier, would be pressing it with a pancake press or any kind of stainless steel die presses. In order to hold it, because there's like no shape for it to go through, is to use an aluminum ring, pour the powder in directly, and then just sandwich it and then press it down to 10 or 15 tons. Once that is pressed, it compresses the aluminum ring and be able to bind the sample into the ring, and you can see, you can analyze either side of this. Alrighty, now what if you have a smaller amount of samples? What would you do? So there are these shells here. You have these boric acid shells, have different diameters. We have a 23, a 13, and a 5 millimeter wells here. These will hold typically around 50 to around 200 milligrams or up to maybe 500 milligrams of sample here. It's the same way. You press it with the pancake press, and once it's pressed, it will look something similar to these examples here. You can analyze these directly without a film, and they do hold the sample in place, and you don't have to put any binder to dilute this down. So these are very simple to use, to make, and you can also recover these samples back.
And that's what we use for our carbon, nitrogen, oxygen analysis.
Right, exactly.
So that it can look at just that sample. If you had a sample that needed a little bit of binder, this provides that support without having to have binder mixed in with your sample.
Right. All right, so here's another way to prepare a loose powder in a cup for a residual callus without pressing it as a pellet, that what we've seen before. So what I have here is a funnel type cup with the bottom of the cup and the cap. So to prepare the cup, we would just put any kind of film that you have, press the bottom of it to the cup, and now you see that it could be easily used to put the sample in. And you can see that is a funnel type cup, that it will just funnel the powder down. So what I have here is a small balance. Then we're just going to tear this and put some powder in. You would only need about maybe 20 to 30 milligrams here.
Just depending on whatever your calibration method is requiring.
Exactly. So we have about 30 milligrams right there.
The nice thing with the XRF is if we add more sample, we can get better detection limits depending on the instrument that we're using.
So you just want to tap this down so that it will cover the entire bottom of it, and then we're just going to put the cap on. I'm going to tilt it a little bit so you can kind of see that it is covered, the bottom of it. And again, you can use this on our next DE system or any of our floor models. And if I tap it, you can see that the powder is still loose. You can recover it after it's analyzed.
Now for this case, we can't do our carbon, nitrogen, oxygen analysis, and that's because we'd be going through the film. So we'd be actually measuring carbon, nitrogen, oxygen in whatever our film that we were using was.
Right, exactly. Okay, so moving on, we're going to go to do liquids. Now, what if you have supernatants in your residual callus? You want to see if it's, purged into the liquid.
Or a parenteral formulation you're looking to analyze,
right.
Any kind of liquid sample. Now, we can do liquids directly into those types of cups. So not the funnel one, but we have straight-walled cups with the film, just the same way prepared, but you could do liquids straight into that. But what Tan's showing right here is we can actually dry the samples down, and we can put directly, we can concentrate it, get better detection limits that way, and then also be able to easily put them on the system, not worry about anything leaking, and run in vacuum, whereas liquids typically you can't do with that.
Right. So we have 3 different types of options here for you to use. This one over here is called the Ultra Carry, where you would put the liquid directly onto the center pad and it will bead up. So this will hold about 500 microliters. To another option that we have here, this is called the Micro Carry. It's basically a filter paper with wax bridges on there. So what the wax bridges does is it'll keep the liquid right in the center of it. So this one uses about 100 microliters of sample. And then the traditional way is just a Wattman filter paper. This is like a 42.5 millimeter diameter. All right, all of these will use roughly half a mil. You should not have to use any more than that. So let me show you how to prepare these really quickly. So I have 250 microliters on my pipette. As you can see, if we zoom into over here, that this will bead up. This is just water, just to show you. You can use up to 1/2 ml, like I said. You see that's beating up there.
And it'll stay in the center.
Right.
And by the way, we tend to use ICP standards, the liquid standards, to make calibrations with these. So you could make a direct calibration. We can also use them on our semi-quant program. There's actually a window in there designed just to run these types of filters. So it lets you put in the volume, or lets you put in a weight of the residual dried material, and then it will calculate the original concentration of the liquid based on that, and you can decide whether or not you want to report it as ppm or mass percent.
Right. So once I've pipetted all my samples on here, you would just stick this in a vacuum oven or an oven, and we can just dry it down. So let me just take one over now so you can see what we're using here. These should go fairly quickly. It should only take a couple of minutes for these. So here I have this vacuum oven. And we would usually put this around at 60 to 70 degrees for a couple of minutes. That should dry very quickly because I only have around 200 to 200 microliters in there. Once it's dried, you can analyze it directly, again, straight in vacuum. You do not have to do this under helium. There's no film involved, and there's a very small amount of sample. So this is great for when you are doing any kind of residual catalyst screening on this, where the supernatant is. If it's in there, you'll see if it's purged it out or not. Okay, now that we prepared our samples in the prep lab, we've now moved over to our instrument where we'll show you how simple it is to load up the samples and run them. And we're showing here the easiest prep here, which are just the pills.
So we've made these things, we basically, made that powder at each of the concentrations, and then we pressed them in individual pills so that we would be mimicking what calibration you do. As long as you can calibrate like that, you could just ultimately run your samples just by pouring in the way Thanh going to show you right now with the calibrants.
We've already went ahead and prepared these cups with the films, so just make sure all the films are the same the way you're going to calibrate them. And all we're going to do is just pour them directly into the cups for each one, for each of the concentrations. You can see it's rather simple and could be quick. Once the calibration is made, you would do the same thing for the unknowns as well.
So that's literally your prep right here. Pour them into a cup, put them on the machine, and analyze. So right now what we're going to do, of course, is put these on. We're going to make the calibration curve that's going to be saved on the system for years. And actually, this is what, about 4-year-old method, Thanh?
Yes.
And so it's still actually, we can analyze these same samples and get the same results.
You've noticed they've charred a little bit because we've analyzed them multiple times and they're still good to go.
Okay, so now they're going to go on the machine.
Load them up. Then we're going to move over to our instrument and show you how to prepare the method. Okay, so now that we're at the instrument, we're going to show you how to build a calibration method to run those pills.
So we go to Quant. We hit on the Quant button. This is our Quant application builder. This is kind of like your application wizard, but we call this a flow bar here. We just follow along it and we create a method. So we're going to do this. So this, the calibration we ran with these pills before, this is for the class 1 and 2A. Which is your arsenic, lead, mercury, cadmium, cobalt, nickel, and vanadium. And but we're just going to do this with nickel right now because nickel is one that we just to show you as an example. But if you're going to do that here, you just pick all the elements in the one method and you do the same thing that we're doing with the nickel. But we're just doing this for time's sake so you can see it live, so you can see it actually happening as we're running it. So we're going to create a new application. If you wanted to, if you hit set analytical conditions in automatic, it actually goes through a process where it'll run scans of everything. It'll make sure that you're not missing anything. It'll suggest overlaps and basically do all the things that if you're not an expert in XRF, it'll go through and do all the things for you. We're just going to create our own. We're going to do it as a powder template. Although if it's a pressed powder or tablets or whatever, it all goes under kind of the powder category. We then have options for different diameters. So if we wanted to get more signal, we could do a little bit more sample, go to a 35 millimeter diameter. If we had less sample, if we wanted to pinpoint or do mapping, we do these smaller diameters. So our standard is 30. That's what you saw loaded on the system right now. And we talked earlier about empirical and fundamental parameters. We can pick and choose those here, but we can also go back and reprocess a method after we've done and change it without having to rerun things. Okay, so this one we'll just call it as Pharma Pills, and we'll do this one nickel, just so that you'll see the whole thing in action. Okay, we're going to put this under Pharma folder. Once that's done, we just go in and we're going to select our elements. We can do them as oxides, as compounds. So let's say you're doing it on an API. You could put within our compound table and utility, put what the stoichiometry is, basically put your formula in, and then say what analyte. So if you had a fluorine in the molecule, if you had an iodine, if you had a bromine or chlorine or sodium salt, etc., you could put that in, and it will just calibrate then on that analyte, but count it as your compound. Okay, so for this case, we're just going to put in nickel. We can put a balance component in. It's not going to really make a difference for this because we're just doing it as empirical method, but I'd hit special compound, I'd go to carbon, and here's cellulose. Add that in, that's my balance component. Okay, hit next. So that's set up. If we're using binder, if we were doing special things on the method, we can put that in here. The only thing we're saying here is to do it in a cup with film, and the film is a 6 micron polypropylene. Okay, so that's just for a notation. Somebody will know in the future how you set it up. In addition, let's say we're doing different amounts of sample each time. We could actually put that and have it correct for mixing ratio. Okay, so now we're going to enter in the standard values, and we could type in these one by one. But the nice thing with the software is many of the features in here are Excel compatible, so we can go in. So right now I can just go back to where my standard values are, and I can basically copy them and then paste all of them in. So I have a blank standard 1 through standard 5, which are at the 1 gram daily dose level. So our 1J is 200 ppm for nickel. Now again, I would be having all of the elements lined up here if I had my class 1 and 2A, if I had selected those under the component selection. So that's how you would do your method if you're going to include all of the elements. In this case, again, just for simplicity, we've just run a nickel so you can see it in real time. So if we hit next here, we have our average composition, just making sure we haven't misplaced a decimal. Of course, our balance is cellulose, so it doesn't really matter. All right. And then when we say next, now any of these along the flow bar we can go back and forth to, but this goes through the logical step of a calibration method. And as we talked about in the first section, the instrument knows what crystals, what kind of things to put in, and so there's default conditions already in. And then as a default as well, it's decided it's going to use the nickel K alpha line, but we can change those as well. All right, so if I go into measuring conditions, if I double click here, it opens up where I can change around all my measuring conditions are. Well, we can change our voltage, our current, we can change what our filters are. In fact, I'm going to put in the aluminum 125 filter in. It's going to give us a better background. And I can change around if I was going to use different crystals and slits and so forth. Okay. The only other thing we're going to do here is we're going to increase our power, get more signal. So I'll go at 50 kilovolts and 75 milliamps. Again, we're at 4 kilowatts. I can go all the way up to 4. We normally run just a little bit lower because we're going to get plenty of detection limit.
And what Glenn is showing here is just basically how to optimize the conditions. But if you go with the defaults, that should be fine as well. And there are, you can see a lot of different parameters in here, but that's specific to this method.
Exactly. Now, if we wanted to have this be a semi-quant analysis, I could change it from private to a library if we were doing an FP application. Okay. So I'm going to say OK here. It's put in those different changes. And then what we're going to do is the next thing is it'll run a scan for us. Now, ultimately, with your method, we're just going to go to a peak position, go to a background, get a net intensity, and we're going to get a result. But with this, in order to optimize it, what we would do is we will run a scan. So I hit. Okay, so now we're doing our optimizing conditions. And what it does here is it says, hey, let me help you out. Let me look at your standard table, and I'll find the maximum and minimum of nickel and all the other elements, and I'll load them up on the instrument and then start running those so you can optimize where your conditions are. So if I say search, it says, yeah, my blank's in A1, and then my standard 5 Tana's put in a 6.
Now the software knows this because you've already entered in this information in the standard samples with all the concentrations.
Right, and then I'm going to say spin sample because these are little pills all randomly oriented. I want it to be spinning around to give me the best data. Say, okay, now this take me 6 minutes. I'm going to speed that up a little bit. You might keep it at that same time. We're going to make it be like 20 degrees a minute. I want this to be a little bit faster so we're not waiting around. Our scan won't look quite as good, but that's okay for this purpose. Okay, so I have those set up to run. There's one scan for the detector window, the energy window, and there's one for the actual 2 theta scan. So if I hit start,
so we're just going to go ahead and hit start here so they can start the scans for the blank and the standard 5, and once that's completed, we'll be able to pick the peak and background positions and the counting time for this particular method. Okay, and you can see here on the spectrometer status, it's loaded up the A1 position, which is the blank. It's going to pump it down. It's going to move it over to where the X-rays are to start analysis.
okay, so in just a matter of minutes, it finishes the scans here for the nickel. Okay, and it'll remove the second one that's done. You'll see it's in there, and you'll hear probably behind me unloading the sample. But what we can see as it's still running, and if we had other elements set up, it would be running those. We're going to finish doing this, optimizing the scans. Now you can see our blank, no nickel there. If I want to look where nickel was, I can do an element search. Nickel should be right here, and we see there's no nickel in the blank sample. Okay. Now, if I go to the scan that had the 200 ppm, this was our high level, you can clearly see a nice good nickel peak there. And if I want to overlay those, see where my background is, I could overlay that one, or if there were other ones, I could overlay those as well. Now this, okay, if we were to look here and do an element search, this is our K beta peak. So if I look, there's the nickel K alpha, and if I were to look at all my lines, I'd see the various lines within that K alpha peak. And if I go and I do a 2 theta search, I can see, well, what element would this be right here? Well, that's my cobalt K beta, and here's my nickel K alpha, and then I would have, down in this region, my nickel K beta. So what we're going to do is we're just going to optimize where those peak and backgrounds are. In this case, because the background's so low, I may decide, well, I want to skip a background altogether. But just for the example, I'm going to put one background point in. Okay, we're going to do the 1 or 2 point background setting. We can do other settings in here. We can do coefficients, but that's not necessary for most of these kind of applications. Now, I'm going to show now, this is at a slope. So if we want to make sure that we're not worried about that, we'll put 2 background points in. So I'll put a background here and here. I'm going to do that 1 to 2 point background setting. And now I have my background, because at the lower levels, this slight variation here could make a difference. So if I want to go down to sub ppm, now that's not a worry for the pharmaceutical application, but for other ones where you're trying to really get down to sub ppm of nickel, you're going to want to build that type into the calibration. So all I'll have to do here is accept those results for the background points, and then what we would do is we would optimize where our peak position is. It'll look at that scan, it'll put the peak position in, and we'll just save that as well. And the last step we're having to do, as we said on the first part, is just set where our analysis time is. So the 2J level, the 1J was 200 ppm, the 2J level, this is 400. It's going to now say, well, based on this kind of counting time, I have a detection limit of 0.3 ppm, so which means I could quantify below a ppm. Of course, our lowest standard here is 20 ppm, because that's a 0.1J level at the 1 gram daily dose. So if I wanted to, I could just say, well, you know what, let's not waste that much time on nickel. We'll do 2 seconds at each of the background points and 5 at the peak. And now our detection limit is 0.6 ppm, which is still well within, you know, the what we need for quantification at the 0.1 J level. So I'm going to stick with that. If I added other elements in, you could see how, you know, for most of the elements you're looking at just a few second analysis, and then, you know, for the ones that we're wanting to get down to lower levels, we would maybe even count for a minute on that element. So I'd say okay. I'm going to save that then. Okay, those are my new saved times. And then what that does is it basically just populates my parameter table here. So you see it change those peak and background positions. And so now that's my kind of final method conditions. And the final thing we would do within this optimizing scan is we're going to optimize where our detector window is. So this is higher order radiation. We don't want to see that. We can narrow this down in a little bit, okay, and look just at making sure that we're just getting the diffracted main peak, right, of the nickel. But where it is set right now is fine, so I'm not going to change that. So next is, well, we've optimized our method. All we have to do is run our standards. So I'm going to hit run standards. It's going to say, hey, you got these standards that you put in the standard table. Do you want to put these on the deck right now and run them? Say sure. Let's do all of them. Start in position A1. That's where our blank was. Do I want to do repeat time? So I want to make sure that I get my calibration curve, you know, really good. Ultimately, my samples I'll do with just one analysis time, but I would improve my, let's say, my standard analysis. We're going to be fine with one repeat, so I'm just say OK. Have that on here, and I will hit analyze. Okay, so we're going to let that go. You can check after it starts running the samples. You can see what your completion time is going to be, and then we can, you know, start processing our linear regression. The instrument's going to help us do that, and we'll show you that when these standards are finished. Okay, so after it's run these standards, so that went through running the standards, and then the screen that pops up here, this is called drift correction. And what you would do here is you would establish a glass sample, let's say, or something that had nickel in it. We provide these, there's other places that provide these, and you just have something that's in the intensity range of your calibration, in the middle to the high range. And then that way, that what you can do is you establish that as a baseline, and then when you run that again later on, when you run drift correction, you can do this at any time. It will set a new coefficient. Right now, a coefficient is 1 because it's a brand new method. We haven't even established what that standard is. But if you don't do that, you can go on. The systems are very stable without that, but it's best to do that for a method that you're going to plan on running for years and years, and you don't want to have to go in and repeat any of this process and recalibrate. So let's go jump on to calibration, and we're going to look at our nickel calibration curve. Okay, there we go. It looks really good. You can drag this out. You can go in and look at your results. Here we have, actually, this is really good. We have, I know it wasn't planned. This is 5/9 correlation, better than 5/9. You can see that clearly. And that's with those pills just poured directly into the cup. So as long as I have a similar formulation to that, or as we said earlier, if we make this an FP method and we make that formulation components be part of the curve, in other words, add a couple more elements into component selection, then we can keep this method for a long time, use it for a lot of different types of samples, just pour them straight into the cup, analyze them as we showed on here, and you really can't beat that in terms of analysis and prep, especially in comparison to running a final product by ICP where you're having to go through digestion and produce waste and things like that. So, and as you can see, it's really easy to run the samples, and we'll do that in a second. So the only thing I have left here to do is save that calibration. Okay, it'll save that method. It puts a little calibration curve in there to let you know that one's been saved. And we would hit next. First thing I want to show though is if we go in to recalculate, we can even break calibrations if they're a wide span into a couple different lines. We can also look and see what our residuals are. So here's a 20 ppm, we're getting 20.5, 40 ppm, 39.5. So the residuals all are very good. And you know, that's what we expected based on what that OMC scan showed us as our expected detection limit. Okay, so we'll just say okay. Close these out. We've already saved that. Hit next. And the next thing on here is to set limit ranges. And we showed that in the beginning. We just say either the limit range of the calibration curve, which maybe that's 20 ppm to 400 ppm. Okay, we could say how many digits. Obviously, we're doing it down to ppm. Maybe we're going to just do 1 digit or 2 digits for that. Okay, and then of course cellulose, we would say that's, let's say 2 digits. That's just a balance. And then our unit, we want to make sure it's reporting a result out as ppm. Okay, that would be for setting a limit range within the confines of what our calibration curve is. However, you might have a spec limit. So maybe I don't want to set it as 20 and 400. Maybe I want my spec limit to be 30 ppm to 30, let's say, what do you want to do, Ton? Because we're going to run a sample against it and show that it passes or fails.
Do you want to do the low one?
So we'll do it based on our 20 ppm limit, or let's say our 0.2 J.
Right.
So we'll set it as
30 to 50.
the lowest 30 to 50.
Yeah.
Okay. And then what we can do, if we run our 20 ppm, it'll fail because it'll be too high. Okay. And then our or too low. And if we were to do our 0.5 J, it'll be 100 ppm, which would be too high. All right. Of course, you might set that just as what the ICH Q3D limits are. All right, that's it. And you have a method. So the only thing, we just look for that method when we run a sample. And if we're going to do that right now, let's go ahead and run a sample. All we would do is go to our easy analysis screen. It's going to pop up a picture of the deck. And so you can even set your modes of login so that you just have an analyst, and they won't even have access to the calibration. So the only thing they would have access to is something like this. We could even put favorite methods in, so I'll configure that right here. I'm going to go in and set a favorite method. I'm going to delete these methods out of my favorites. I'm going to add in a favorite method under my quant, and I'm going to find our pharma method here. And whoa, I have a lot of those. Here's my pills with nickel. Now that's going to be the method that I will go to. And what it's saying here is that anything that it's set up with other conditions are gone. So here we go. Here, put it in, go to my favorites. That's the only method available here. And if you even wanted to, you can have it configured so the analyst only sees the favorite methods that have been designated. So
this is really good for a quality control environment or open access where they only see those methods that they're going to use. And that's the only things that they will select.
Right. So now if I want to run sample 2 and 3, which was our 20 and our 40 ppm, we can run that.
Which is the 0.1 and the 0.2
right.
J level.
And then all I'm going to do is just name it. So if I go here to 2, I'm going to name that as 20 check. Oops. And this one here as 40 check. I can have it go into a specific folder. I'll just have it in the common folder, or I could switch this to, let's go to pharma. Okay. And then we'll go to 2. I'll make that the same folder. If you had already picked one folder on there, it's going to leave that as a default. So let's say your analyst always wants to run it under their folders, it'll put it in. So that's the method for both of these. And then all I have to do is hit start. It'll load that sample up. It'll start running. It'll put a little countdown on the screen. And then that's it.
Now, while you're running, you can continuously add more samples to the deck.
Right, I could put on sample C2 there and put the same method and do another one. I can, drag that around to the next position. Let's say I wanted to do also a 100 check. Can add that to it. And then if I wanted to now add it to the queue, I just hit start on there as well.
So the samples have just completed, and we're going to show you the results right now. As you can see from the first one, because we set the limits from 30 to 50 ppm, we know that this first one was below that. That's why it's 20 ppm. That's why it's showing it's low. The middle one does not have an X. That means it basically passes because we're within the spec of 30 to 50. And this one is the 100 ppm, which is the higher level, and therefore is higher than the specs that we have. Therefore, is also giving you that it failed. So either it's too low, it's going to be in pink, or too high, it's going to be in red. So that would be as simple just to see how the results would be right away, depending on what the spec levels that you put your samples on. Or if you're going to quality control check something, this will show very clearly that it either passed or failed.
And of course, the samples are saved in the results table. You can't delete those. You know, within here, we can clear analyzed IDs so that we can set up new samples in there, but all the results are saved and can't be deleted. And those can be configured as well with the limit system.
All right, so now that we've already prepared our method and we've calibrated to for nickel, we made it with our round pills here. But what if we go and run unknowns that are oblong? So if you have unknowns made of different shapes, you can still use this method. So all you have to do is just pour it into your cup, bring it over to the system, place it into position B1, and we're going to start the method. Okay, so here's the screen where we had before. Just select your B1 position. Your method's already selected because of what we had said earlier. And then we're just going to run it again. And all we have to do is just hit start. As you can see, it's going to load the sample up right away. And in a matter of about a minute, it should be completed. All right, let's come back over here and check out on the status. What it looks like here. So as you can see, it's pumping down right now. And it should load it into the system. And while it's running, you can add more samples as well. So it could be like a continuous run. Open up the system and just select other methods as well. So it doesn't have to be the same method. It could be different methods you can run. So for a walk-up system, it'd be very easy to load up all different types of methods to run.
And once you have one sample running, the rest of the samples will be loaded up in queue. So it'll load, it'll actually pick up the next sample right now if we had another one set up, so that it's not wasting time doing that kind of exchange of the sample.
Right, so if I select just another position, pick a different method, if we had it here in the favorites, type in the name and just hit start, and it will go and pick that one up and get that ready in queue. So the results here have been done. As you can see here, because we had set our limits between, I believe 30 and 50, this one should be around 80. You can see it's above the limit.
And it's at almost 79 ppm. So
right.
Our actual sample that we made in an oblong shape is 80 ppm. We're getting 79 ppm with a different shape than we've actually analyzed. And all we had to do is pour the pills into the cup.
Thank you for joining us. We hope that you enjoyed our workshop and how easy it was to create a quantitative method, and as well as how easy it was to put any unknown samples on and just come over directly to the method and analyzing it. So if you have any questions, please feel free to contact either me or Glenn, and we will be happy to answer any of your questions. Or if you have additional questions about your particular products, we would love to do a one-on-one session with you. Thank you.